Okay, here we've got the notes for section 3.4, velocities and other rates of change. So this is using the derivative for kind of real world applications. So the instantaneous rate of change, so if you notice this is m, this is the slope of the tangent line, same equation we've seen a lot at a, same equation as always before. Is the derivative blah 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 provided it exists. So you can also use the power rules and stuff like that. Okay, so example 1, find the rate of change of the area of a circle with respect to its radius r. Evaluate the rate of change of a at r equals 5, r equals 10. If r is measured in inches and a is measured in square inches, what units would be appropriate for dA dr? Okay, so for part A, I need the equation for the area of a circle. This, okay? So dA over dr, the derivative with respect to r, so r is my variable, so exponent multiplies out front, 2 pi, I count down by 1. Now pi is a number, so it acts like a coefficient. So this equation will give me the rate of change of area with respect to radius. That's A. So for B, when r is 5, dA dr is 2 times pi times 5, or 10 pi. When r is 10, dA dr is 2 times pi times 10, or 20 pi. So if you notice, as the radius gets bigger, the area grows faster. So this is how much the area is increasing due to the radius. So for part C, dA's area, so that's inches squared per radius, which is inch. So for every inch, essentially, so when it's 10, for every inch the radius grows, the area grows by 20 pi. But this number is different. Because if you think about a circle getting bigger, if you increase the radius, I'll draw a picture. So here, so if I increase the radius, same distance, so there's this ring, and then this ring. So even though the widths of those rings are the same size, the outside ring has much more area because it has to go farther around, which is why the area increases more the bigger the radius gets. Okay, motion along a line. So velocity is just the derivative of the position function, and speed is the absolute value because speed doesn't have direction. So speeds are like 45 miles per hour. Velocity would be 45 miles an hour south, so on and so forth. All right, so example 2, a student walks around in front of a motion detector that records her velocity at 1 second intervals. So 1, 2, 3, 36 seconds. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So each of these is 4 seconds in order to get up to 36. She stores her graph in her graphing calculator and uses it to generate the time. So this axis is time. The vertical axis is velocity. Graph shown below. Describe her motion as a function of time by reading the graph. So here, so she's speeding up because velocity is increasing. She's walking at a constant speed, doesn't change speed, and then she slows down. And here she's just changing direction because her velocity now went negative. And then, so we're getting more and more negative, so we're walking faster and faster. We'll say away. We'll talk about it towards away. So towards, speeding up, speeding up, speeding up, constantly approaching, slowing down as we come towards it. Then here, we turn around, we walk away from it, and here we're walking back towards to it. So where's her speeding maximum? Right there. So even though it's a negative number, its absolute value is the largest absolute value. Speed is measured by absolute value. All right, acceleration is the derivative of velocity. So a of t, the acceleration, is dv dt, which means it's the second derivative of the position. So these are free fall constants. If you've had physics, these should be familiar to you. So in English units, gravity acts at 32 feet per second squared, negative because technically it's down. Metric units, 9.8 meters per second squared, technically negative because gravity acts down, but if you're not taking direction into account, it doesn't really matter sign-wise. But normally they're negative numbers, which is why here it's a negative value. So a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of this equation after t seconds. How high does the rock go? So the rock goes up, the rock comes down. So the maximum height here, we can find one of two ways. We can figure out how long it's in the air by finding that time when it hits the ground again. We know this time is 0. And then taking half, find the average, and then plugging that into my position equation. Or I can take the derivative, because when you hit the top, your velocity is actually 0, because you have a positive velocity. and then you have a negative, and to go from a positive number to a negative number, you have to go through 0. So I'm actually going to do S prime, which is V, so that's 160 minus 32t, and I want to know when is that 0? So that would be negative 32t equals negative 160. So 160 divided by 32 is 5 seconds. So this thing takes 5 seconds to get to the peak. So now that I know what t is, I can just plug it back in here. So S, 160 times 5, minus 16 times 5 squared. All that fun stuff goes in your calculator. Minus 16 times 25. So the maximum height the rock goes is 400 feet. So we're measuring in feet. What's the velocity and speed of the rock when it's 256 feet above the ground on the way up, on the way down? So I know my position. So 256 equals 160t minus 16t squared. So I'm going to rearrange this equation, negative 16t squared plus 160t. So that equals 0. Oh, whoops, sorry. I need to figure out, yeah, no, I was doing that right, shoot. I need to figure out when is it 256 feet above the ground. So 256 equals 160 minus 16t squared. So that's, we're going to make this quadratic, so negative 16t squared plus 160t minus 256 equals 0. All those numbers can be divided by 16. I'm actually going to divide by negative 16 because why not? So that's t squared minus 10t plus 16 equals 0. So that's a quadratic. Let's try to factor it here. So two numbers that multiply to 16 and add to 10, that'd be 2 and 8, but they both have to be negative. So it's 256 feet above the ground when t is 2 seconds, because that's what that makes that 0, and when t is 8 seconds. So then I can take my times and plug them into my velocity equation. So 160 minus 32 times 2, 160 minus 32 times 8. Oops, 32, 2. So the first one going up is 96 feet per second, and coming down is negative 96, which makes sense, because however fast you are going up, you're the same coming back down. What's the acceleration of the rock at any time t? So acceleration is v prime, which is the second derivative of the position. So if velocity was 160 minus 32t, v prime, which is a, is equal to negative 32, which is actually the English units up here. When does the rock hit the ground? No actual more calculations are needed. So at t equals 0, it's at the bottom. At t equals 5, it's at the top. So it takes 5 seconds to get to the top. To come back down, it's going to take another 5 seconds. So it hits the ground at t equals 10 seconds. Okay, so example 4, similar thing, you got motion along a line, so its position is given by this equation. Find the displacement of the particle during the first 2 seconds. So I need to figure out where it is. So that's find s of 2. So that's 2 squared minus 4 times 2 plus 3. So that is 4 minus 8 plus 3, which is negative 4 plus 3, so it is 1 unit left of where it began. Find the average velocity of the particle during the first 4 seconds. Well, I know where it ends up, so velocity is distance divided by time, negative 1 over 4, so that's just negative 0.25 is the average velocity, distance divided by time. So change in distance divided by change in time. That's how far it goes. 4 seconds is my time. Find the instantaneous velocity when t is 4. So that's the velocity equation. So that's s prime. So that's 2t minus 4. If I take the derivative, so 2 times 4 minus 4 is 8 minus 4. So 4. So it's moving pretty quickly to the right at that time, but that's its average speed. Acceleration when t is 4. So so acceleration is the derivative of the velocity. So that's v prime, which is just 2. So that's my acceleration. Describe the motion of the particle. At what values of t does a particle change direction? So that is essentially this part here is when is v 0. So v is this equation. When is it 0? So that's where it changes direction. So that would be 2t equals 4. So it changes direction when at time 2. So it's going kind of like that. Okay, sensitivity to change. So we've got this equation, compare the graphs of y and dy to find what values of y are most sensitive. So I need y prime, which is going to be p minus 2p. When you graph this, you have to use x's though. So menu, graph, so the y equation is 2x minus x squared, and then I have, oops, that's not right. That should be 2. Derivative of 2p should be 2. So that's going to be 2 minus 2x. Draw. So if the derivative measures the sensitivity to change, when p is very small, the derivative is very large, so it's much more sensitive to change, which makes sense. Now, if you put just a couple plants in, it's going to affect it a lot more than if you already have a bunch, and so on and so forth. What values of y are most sensitive? So to changes in p, well, so small values are most sensitive. All right, in economics, you have what's referred to as marginal cost and marginal revenue. So marginal cost is essentially cost of making one more of something. Marginal revenue is how much money you would make if you sold one more of them, but they are based on the derivatives. So the cost per item, the revenue per item, which is a derivative function. So marginal cost is going to be c prime. So c prime is 3x squared minus, 12x plus 15. So exponent out front, count down by 1. Exponent out front, count down by 1. Exponent out front, count down by 1. Marginal revenue is r prime, the derivative of r. So that is 3x squared minus 6x plus 12. Exponent out front, count down. Exponent out front, count down, blah, blah, blah. So we're making 10, so I need c prime of 10, and I need r prime of 10. So this is 3 times 10 squared minus 12 times 10 plus 15. So this is 300 minus 120 plus 15. So that's 180, that's 195, I think. 300 minus 120 plus 15, so that's 195. Over here, we've got 3 times 10 squared minus 6 times 10 plus 12, so that's 300 minus 60 plus 12. So that's 240 plus 12, so that's 252. So what this is saying is that it's going to cost me another $195 to make the additional radiator. But I'm going to sell it and I'm going to make $252. So I'm still coming out ahead. So eventually these numbers will trade places. This will become smaller than that. And that's when you're starting to produce too many, because it's costing you more to make the thing than it is you're going to gain from selling it. Which brings us to the end of this section.